Suppose I take a piece of metal, thin metal, like an aluminum sheet, or like aluminum foil, and I cut two slits in it, two vertical slits, okay, like that. Alright, so this is supposed to be a kind of a 3/4 view, and behind it I shine a laser onto those slits. Well, now that we know that laser light is coherent light, and we can think of it as plane waves, we know that as it comes through these slits, if they're small enough, similar to the wavelength of this light, then the light will diffract through each one. Okay, I'm going to draw a different view of that. I'm going to draw a different view of this as if I'm looking straight down on the top of it, right through the center. So we have this slit that looks like that. We have really thin slits, okay, and they're spaced apart by some small length, and we'll talk about how small that has to be later. Okay, so here come my plane waves coming onto it. All right, and the light hits these slits, and we've learned, so as they come forward, we've learned that they're going to diffract through it. So if I get one there, then I'll get another wavelength curve part here, and another wavelength curve part here, and just keep going. It's going to spread out. I should have made that equal length. And this one's going to have the same thing. You have that there, and then I'm going to have that there, and there, and like that. Okay. So these are starting to interact with each other now because they're overlapping. And so I could look at all these knowing that each one of these lines represents a crest of a wave. Then everywhere two lines intersect, it's going to be crest on crest, and I get constructive interference. So like right here, we can see in the middle of these, because of the symmetry, that should be symmetric, we get this line where they will always intersect. Okay. Then off that line, we also get points where we get crosses, and they're gonna have constructive interference there. So any point where we get these lines crossing over is going to be a point of constructive interference. Okay. Now, any point where you have a line in between the lines of another wave, that's going to be destructive. So I can draw like an X there, or an X there, or an X there, because in between this one and this one, right in between, that's a valley, but this line is a crest, and so those would be a crest on valley, which would give me destructive interference. The question I have is, if I were to project this all the way to a distant wall or a piece of paper that's far away, what would I see on that wall? So I have to imagine these are now traveling really far. So I'm going to draw this a little bit smaller, not too much smaller. I'm going to draw like this. Okay. And again, these waves are coming in here. And I'm going to just choose one kind of direction, like this one's going that way, and this one is going to go, and they're going to meet on that wall at the same spot. So here's my wall. I draw it over here, and we're going to assume this wall is really far away, and I'll explain why or how that helps us in a minute. Let's suppose that light from this one travels upward and hits a spot on that wall right there. Now, light's going everywhere, so light's coming from here and hitting everywhere, just like these curves are just going everywhere. But we're just going to focus on that one ray that hits that one spot right up there. And we're going to assume there is a ray from this one that also gets up to that spot. Okay? And just to give ourselves a reference, I'm going to draw kind of a midline here. Okay, so this is like the middle of the slit, straight ahead. Okay. And so I can ask myself, at that spot up there, we'll call it Y, how do I know if it's bright or dark? You know, is it constructive interference or destructive interference? Well, we know since these are laser light, which means coherent, which means the light's in phase, we know that as they come out of these slits, they have the same phase. So all we care about is the path difference from there to there. And, you know, if I draw a line from this slit that intersects this one perpendicular, and I remember that this wall is way, way far away. Okay, and this height isn't really that too far high. Then when I look at the length of this one, we can call it R1, and then the length of this one, R2. Well, from here to here is nearly the same as R1. And so when I look at delta R equals R2 minus R1, what that is just this piece right there, from here to here, because this piece is about the same length as this one. Okay? So my condition of constructive interference is I want delta R to equal lambda, or 2 lambda, or 3 lambda. We'll just focus on this and add the possible higher orders later. So my question is, how big is this? And then once I do, then I can determine what angle it's going to be, and therefore what height up here I'll get a bright spot. Because this again will be constructive interference, this condition of being an integer number of wavelengths. Okay, so with that, we need to create a couple triangles here. One is this triangle that we can see here. We can say, let's say the distance between the slits is d. Okay? With that distance being d, and if we define an angle theta here, then this path length here, this delta r, is equal to d sine of theta. Alright? So that's our situation, and we want it to be constructive, and so that's going to be equal to lambda, or 2 lambda, or 3 lambda. And so we can represent that with an integer, which I didn't leave enough room in front, but I'm going to put it behind. I'm going to put an m, with m being 1, 2, or 3, or 4, all the way up. Okay? And so this is our condition. Now that's not too hard. We can usually control this. We usually machine something to control this, or we could inspect it with a microscope and see how big this is. Now theta, how do we understand what the theta is? That can come from this experiment over here. First of all, knowing that this is super far away means that if we draw kind of a line from the center all the way up to that and draw an angle from that to this reference line, that angle there is, to a very good approximation, the same as that. If you rotate this by 90 degrees, you get that angle. Okay, so that's great. So we know that theta is the same as this theta. Well, something that I can control is I can control how far apart these are. So I'm just going to say, that arrow's pointing all the way to here. So this distance from the wall to the slits to the wall is L. And then lastly, I can measure this. I can see where straight ahead is, and then I can measure up to where this bright spot is, and so I know why. Well, looking at that triangle, I'll redraw it here. I have that theta, L, and Y, and I've got tangent of theta equals opposite, or Y, over L. And so that way, on this wall over here, measuring Y, measuring L, I can then find theta, plug theta into here, and then using sine theta, and then multiplying by this thing, which I can control. I can machine it, or I can measure it with a microscope. That allows me to be able to determine what the wavelength of my light is. And what's really cool, before we continue on with this specific example of double slit interference, is what we just did, that idea of using some of these measurements to find the wavelength, is called spectroscopy, one of the most powerful research techniques I think ever. It is used in so many different ways, both from medicine to astronomy, all sorts of different things. Allow us to determine different properties of light, different wavelengths of light that are themselves indicative of material properties and other things. And so this is the basic idea of a spectrometer, which we will use in lab in this course. Okay, so back to this particular problem. So these two bits of information here, I'm going to go and box them in, allow us to then be able to calculate various things. If I measure where the spot is, and I know how far the screen is, this wall, piece of paper, or screen is from the slits, I can find theta. Plugging that in, knowing D, I can then determine the wavelength of light I'm going to use. Or let's say I know the wavelength and I'm trying to use that to measure how big B is. I can go backwards, still finding theta in the same way. I can plug theta in there, plug lambda in there, and then solve for d. So this allows me to find these unknown values. Okay, we're going to take this one step further before leaving and say, well, very often we're measuring very, very far away, and because the wavelengths are so small, we don't have to go very far away from here to get the first bright spot, the next one associated with 2 lambda, and so on and so forth. We don't go very far. So if the screen is like many centimeters away, even meters away, if that's true, and this is not very far, we're talking millimeters to maybe centimeters far away, then this theta is a really small theta. It's super small. I've totally exaggerated it here. So if I were to redraw that experiment, my slits are so small I can't even see them. They're super small. And I'm over here, and I get this really narrow triangle, and theta is super small. Okay, you can't even draw it. That's my super small theta. When that's the case, when theta is super small, there's an identity that we can use. It's an approximation, and it works really good, again, if our screen's super far away, on the order of many tens of centimeters, if not more than a meter. Okay, and that is that tangent of theta is pretty darn close to sine of theta. Okay, and if that's true, then tangent of theta equals y over L. I can take that, plug it in for sine of theta, and I end up with an equation that says dy over L equals m lambda. I'm going to put that integer in front now, where it's a little bit more straightforward. Okay, so dy over L equals m lambda. Now, usually we're trying to look for lambda, and so we can say that the wavelength of our light is going to be equal to, dividing down by that m, dy over ml. Or sometimes we're trying, knowing the wavelength, we want to see where the spot, how far up it's going to be. And so we can solve for that, and we get y equals ml lambda over d. So these are all useful just depending on what you're looking for. These are also useful and don't employ an approximation. Okay, so it's important to recognize that this does assume that the angle is really small. Very, often the case. Therefore, it's a useful approximation, but it is an approximation. So this is now our relationships. We can find the spots of positive or constructive interference. We measure the length of the screen, the width of the slits. We know our wavelength of light in this case, and then we're just counting up how many wavelengths have we done. We get one bright spot, then another one, then another one.